Boom, recording. So as usual, if you are not interested in having your voice recorded, then send me a chat, but I won't be able to get the chat because I'm in PowerPoint. You'll have to wait till the end. So anyway, this is last lesson. I don't know why this is still up. Boom. All right, so we're dealing with fluids now. So the fluids, the first type of fluids we're going to look at are static fluids, and that's what we're dealing with today. And then we will look at dynamic fluids, or fluids in motion. So fluids in motion, or fluids at rest. That's what the word statics means, fluids at rest. Liquids and gases are fluids. And a fluid is anything that flows. Density, I don't know if we talk too much about density, but density, the symbol for density is the Greek letter rho. I write my Greek letter rhos like this. It looks like a lowercase p. So, and it's like a curvy p like that. Not like this, a curvy p, but I always put a little tail on the end of it so I can differentiate it. So when you see this symbol over here, that's a rho. That means density. And density is mass per unit volume. And the units, kilograms per meter cubed. So volume, right? A volume of a rectangle is length times width times height. Volume of a cylinder, pi r squared h. And volume of a sphere, 4/3 pi r cubed. Those are our volume formulas.
What's the difference between the kilograms per meter cubed and the rho? Like, it seems like you're trying to say it's the same thing.
Well, this is the symbol for density. These are the units.
Oh, gotcha.
Any other questions there? All right, so let's just try a volume problem. Suppose you have a coffee mug with a cross-sectional and vertical sides of uniform radius. What's the inside radius if it holds 375 grams of coffee when filled to a depth of 7.5 centimeters? Assume coffee has the same density as water. So here's our density chart. Water is here. And notice these are times 10 to the third. So the density of water is 1,000 kilograms per meter cubed. So that's our density of water. So how many centimeters cubed is that? Or grams per centimeter cubed? What is it in grams per centimeter cubed? Anybody know? The density of water in grams per centimeters cubed is 1. And 1 gram per milliliter too. All right, so 1,000 kilogram over meter cubed. Remember, 1 kilogram has 1,000 meters in it, times 1 meter cubed has 100 centimeters in it. So you'd have to cube that. So that gives me 6 zeros up here, 6 zeros down here. 1 gram per centimeter cubed. So let's get back to our problem. Here we have grams and centimeters. So I just told you the density of water is 1 gram per centimeter cubed, and that's a constant. You don't have to show that. You can just write it down. We know our mass is 375 grams. We know the height is 7.5 centimeters. What shape is a coffee mug?
Cylindrical.
Cylindrical. So we know the volume is pi r squared h. And what's our goal? Find the radius. So our goal is to find r here. So the density of water equals the mass of the water over the volume of the water. So let me rewrite this. VW equals mass of the water over the density of the water. Pi r squared h is the mass of the water over the density of the water. So h equals mass of the water over pi times r squared density of the water. Follow me? Did I go too fast there? So now we can just plug it in. Let's move this up here because I ran out of room. H equals 375 over pi. We're looking for R, aren't we? Man, it didn't take me long to screw up today. I didn't want to erase this either. Let's just undo. I can't undo. Darn it. Sorry, we're looking for R, not H. So that means pi r squared h, mass of the water over the density of the water. R squared equals mass of the water over density of the water, pi h. Move it up here now. R equals the square root of 375 over 1 times pi times 7.5. What's the radius of our cup? Four centimeters. So 4 centimeters is literally like that long, maybe longer, that long, pretty somewhere in there. That's about the size of a coffee mug. I mean, obviously your screen's gonna be a different size than mine, so whatever, that might have been, well, that's a little big, but that's the idea. This probably wasn't the most effective. And this is the radius, so 8 centimeters. If you think of pencils like 10 centimeters, a short, not a long pencil, like a lead pencil is like 10 centimeters, like a Bic lead pencil and the clickers. So half of that, that's about the size of a coffee mug. Anyway, that's how it's done. Any questions on that? Anybody? All right, so that's the density chart we went over. That's in your book. If we ever need a density. Some more fluid statics. Pressure. Pressure is force over area. And this is surface area. That's your surface area. So you can see a finger pushing on your arm with the same force as a hypodermic needle. The needle's going to have more pressure because it's a smaller area. Now, this is something right here that you may not be familiar with. That's a Pascal. So the units for pressure are pascals. And a Pascal is 1 Newton over a meter squared. So when you see pascals, that's newtons, which is force, over meters squared, which is area. Anybody have any questions there? All right. So give this a try right here. You should be able to do this. Notice this is on 2 lines. Oops, I didn't mean to put a strike through. One millimeter diameter. 1 millimeter diameter. And our area is pi r squared. I'm gonna go check the chat, see if anybody left me a message. No, no messages.
I got an answer.
Nice. That's what I like, answers. How about the rest of you?
I got something.
Alrighty then. So P equals F over A. And what's it say? We given the pressure and we're looking for the force. So F equals P times A. F equals 3 times 10 to the 9th times pi. Well, 1 millimeter diameter. So that's 1 point. The radius then equals 1/2 a millimeter. So the radius is 0.5 times 10 to the minus third meters. So 0.5 times 10 to the minus third squared. And we just jam this into our calculator. And I got 23.55. How did we do?
That's what I got.
That's what I got.
Nice.
Yep.
I can't
Anybody
believe
have
the
anything to
reactions were
clarify?
taken away.
What's that?
So the reactions were taken away. I was gonna hit you with the thumbs up.
I know I can't see it anyway, but thanks. All right, next. Fluid statics. Still talking about fluids not moving. Now that was the pressure of that. A pressure in the fluid is due to the weight of the fluid. So this is the formula with that density in it, where P equals rho of the fluid GH. That's how we write it. Notice my fancy P. That's actually a rho. So what happens is this fluid has a weight in it based on how deep you are. So the fluid above you, if this is like a giant pool you're swimming in, the weight of the fluid directly above you is what causes the pressure on you. It's like a big weight pushing down on you. The weight on the sides over here, this weight doesn't matter. None of this, because it equalizes itself out. It's only the weight directly above you that causes what you feel. So like when you're swimming and you go to the deep end of the pool, you feel your ears pop because the weight of the fluid pushing down on you pushes in on your ears. That's what happens there. So when you stick something in a fluid, and the fluid can be air, it has that weight pushing down on it. So here we are with air pressure. Remember, we said air was a fluid. So air pushes down on you while you're on the ground. So if you're standing here you are in this little bubble, and the air is actually physically pushing down on you. Again, the air on the sides doesn't matter. This air doesn't matter. It evens itself out. All this is at the same pressure. It's only this air coming down on you, on top of you, that causes the pressure. That's it. Standard atmospheric pressure at sea level, we call it PATM, is equal to 1.01 times 10 to the 5th pascals. Sometimes I'll write it as 0.13, right? Just because that's a habit from my younger days. This book uses 0.10. So if you see me write it out to the thousandth place, don't get all wound up. It's just actually a good habit, but it's just a habit. So the pressure of the atmosphere pushing down. Now, let's say you have a bucket of water down here, right? Well, the pressure down here at the bottom of your bucket has the pressure of the atmosphere on it, plus the pressure of the water. We call that absolute pressure. And we have a slide coming up on absolute pressure. But the absolute pressure is the pressure at the bottom of everything. This pressure right here, the pressure in the fluid itself, in the water, that pressure is what we call the gauge pressure. The gauge pressure. So like when you're taking the air pressure on your tire, right, you have one of those old school things and you put it in there and the needle pops out. It has the readings on it. You know what I'm talking about?
Tire gauge.
A tire gauge, yeah. So a tire gauge, when you put it on there, that's reading the pressure inside the tire. And this has to overcome, this needle part has to overcome atmospheric pressure to pop out. So you're just reading the gauge pressure there, the pressure inside the tire. So anyway, that's the difference. We got absolute pressure and we have gauge pressure. And here's a picture. Gauge pressure is relative to atmospheric pressure. Absolute pressure is the total pressure, the sum of the gauge pressure and atmospheric pressure. Gauge pressure is without atmospheric pressure. Any questions there? Any questions? All right. If you dive 30 meters below the surface of a freshwater lake, what is the gauge pressure and what is the absolute pressure? So remember, the density of water, 1,000 kilograms per meter cubed. That's something you need to commit to memory or have it handy when you're doing the tests and the quizzes because it comes up all the time. First question says, what is the gauge pressure? Pressure equals the density of the fluid times gravity times the height. Notice this formula. Does it look familiar at all? Remember U equals mgh. This was potential energy. The pressure is like the potential energy. So when you have, this is just mass over volume, GH. And this is force over area. So remember, area times height is your volume. So see the relationship there? So anyway, there's just fun physics, how it all relates together. So to find our gauge pressure, P equals 1,000 times 9.8 times 30. I guarantee I'll have a test question where it asks for gauge and absolute. I can't guarantee it, but there's a good chance that this is going to come up again at some point. Very common question. So 1,000 times 9.8 times 30. (2.94 times 10 to the 5th newtons per meter squared. Or if you want to be fancy or correct, I should say 2.94 times 10 to the 5th pascals. That's our gauge pressure. Absolute pressure is P absolute. We could put a G over here if that helps you, pressure gauge. P absolute equals pressure of the atmosphere plus rho of the fluid, GH. Essentially, absolute pressure is the pressure of the atmosphere plus the gauge pressure. So the pressure absolute, 1.01 times 10 to the 5th plus 2.94 times 10 to the 5th. The absolute pressure is, should be able to do that in my head, right? 3.95 times 10 to the 5th pascals. Any questions there? Anybody? All right, moving on down the line. Oil and water do not mix. A layer of oil is 6.5 centimeter thick, floats over 80 centimeters of fresh water. If the density of oil is 0.75 times 10 to the 3rd kilogram per meter cubed, what's the absolute pressure on the bottom? So we're looking for the pressure down here, folks. Give this one a rip. All right. How we doing out there?
Good. Give me a couple seconds.
Okay.
Okay.
Anybody else need another minute or so? We good? Speak now. Forever hold your peace. All right. So we got the absolute pressure. We want the pressure in the water, pressure in the oil, pressure in the atmosphere. So the absolute pressure is going to equal rho of the water, GH of the water, plus rho of the oil, GH of the oil, plus 1.01 times 10 to the fifth. Pressure absolute equals 1,000 times 9.8. The height of the water is 80 centimeters. So that's 0.8 meters plus 0.75 times 10 to the third, or what we like to call 750. 0.65 plus 1.01 times 10 to the fifth. Pressure absolute is yeah, 1.09 times 10 to the fifth. Is that right? Feels like I did something wrong.
That seems way too large.
No, it's got to be to the fifth.
Yeah, I mean, like, I got 1.010837.
Times 10 to the fifth.
Yeah.
I got the
Oh.
1.09, so I don't know if I did something wrong.
All right, hold on. This crazy RPN calculator. .09 times 10 to the fifth. I got it again. So it's got to be right. This was like 7,800, and this is like 450. Anybody have any questions on that?
I put 101 times 10 to the fifth. That was the problem.
That's all right. I multiplied them one time when I did it. I had to tie the 55th power. I might have typed in 55. All right. Next one. We got a lot of different stuff going on with fluid statics. This is Pascal's principle. F1 over A1 is F2 over A2. Essentially, Pascal's principle tells us pressure 1 equals pressure 2. The pressure is transmitted undiminished. Now, that's a big word. That means without loss. So pressure is transmitted without loss to all portions of the fluid into the walls of the container. Like a toothpaste tube, right? You got a tube of toothpaste and you got your little hole at the front and you squeeze it back here. You apply the force. It pushes it through there and then it comes out with the same amount or with a bigger force because the area is smaller. So the amount of force, if you like hammer it down with your hand, it'll shoot out super hard because that area is restricted where the nozzle is. So when we were little, we would take Barbasol cans and we would melt needles in the Barbasol can. And then you pull the needle out and the Barbasol shoots like 30 feet. Did you ever do that? Like shaving cream, Barbasol. Anybody ever do that? You guys are too busy on your phones to have fun outside.
You had an interesting childhood, sir.
Hey, sorry.
Hey, you were probably born before electricity was in houses.
That's really funny. It's really hilarious. Use that phone to realize when electricity was in the houses. Let's try a problem now that I'm angry. Now, look, one thing here. If I had to push all this fluid down, right, notice the cross-sectional area. Over here, I have the same amount of fluid, but I don't have to move it as far, or it won't move as far, because this volume of fluid here is going to equal this volume of fluid here. It's just stretched out. You know what I'm saying? So this one goes a much greater distance. And this goes back to our conservation of energy. The work input has to equal the work output. So I'm moving all this water and it's going over here, but now that it's stretched out, it doesn't go as deep. Does that make sense? Because you're only moving the water. You're not moving extra water. So we're not, the conservation of energy is holding true here. All right, so what force must be exerted on the master cylinder of a hydraulic lift to support the weight of a 2,000 kilogram car resting on the slave cylinder? The master cylinder has a 2 centimeter diameter and the slave has a 24 centimeter. So what force we're looking for? So our force 1 is 2,000 times 9.8, 19,600 newtons. And the slave cylinder has a 24 centimeter diameter. So the radius one is 12 centimeters. And I don't have to change that because the other one's in centimeters too. Our goal is to find force 2, and radius 2 is 1 centimeter, which makes it nice. So pressure 1 equals pressure 2. F1 over A1 equals F2 over A2. F2 equals F1 times A2 over A1. F2 equals 19,600 times pi times 1 squared over 12 squared times pi. Pi or squared, but either way. So F2 equals 136.11 newtons. We're in newtons. So you can see we don't have a lot of force here. This is 144 times bigger that we get out just by changing the area. Does anybody have any questions there?
Yeah, so what would the R, like, why is it written as R here, but then in the formula itself is written as an A?
This is area. Remember, area is equal to pi r squared of a cylinder, cross-sectional area. That's a cylinder, if you can't tell.
It gives you the radius and you have to find the area.
Ah,
Yeah.
fair enough.
Yeah, because the area is that. So all I did was substitute in here pi r squared 2 and pi r1 squared. Does that make sense?
It does.
Cool.
Just give me one more second to finish writing this down.
Let me know.
I'm good.
All right, last thing we're going to talk about is the buoyant force. It is a net upward force on any object submerged in a fluid. So this would have negative, can't really see that, negative buoyancy. That means the buoyant force is less than the weight. This is neutral buoyancy. Buoyant force equals the weight. And over here we have positive buoyancy. FB is greater than the weight. So the buoyant force and the weight are related, whether you sink or float or stay at any height, like a fish, or like we could do that by manipulating the air. Neutral buoyant it's called. All right, so, and here I just wrote it out. But essentially, if we draw a free body diagram, the weight of the object is down and the buoyant force is up. The buoyant force. Here you can see it. Weight's always down, buoyant force is always up. And if you only have something partially submerged, right, there's still a buoyant force acting on it. Now, there was a famous guy, Archimedes, who determined how to solve for the buoyant force, the amount. And what he said was the buoyant force equals the weight of the fluid it displaces. The buoyant force equals the weight of the fluid it displaces. So whenever anything is submerged, right, what happens is if I put this object in the water, it pushes all this water out of the way in all directions. If you added up all of the water that this cylinder pushed out of the way, right, this thing here, all this water, if you added it up, and the way you would do that is you would get like an overflow container. I can't really do it for you because I'm virtual, but you got the water in there. You take an object, you put it into the water, and water squirts out. And then in the second one, you collect the water, and then you find the weight of this water. That's the weight of this water equals the buoyant force. So if the weight of that fluid is greater than the buoyant force, the object floats. Like a helium balloon floats. I'm gonna put helium in here. Because the buoyant force is greater than the weight of the balloon plus the helium inside the balloon. So the air that it displaces, because this is the weight of the air displaced is greater than the weight of the balloon plus the weight of the helium. That's why it floats. That's why you don't see hot air balloons floating at noontime in August, because the air outside is just as hot as the air inside. So the weight of the air the balloon is displacing is equal to the weight of the air in the balloon, so you can't lift it off. It's usually in the fall and the spring, in the mornings and the evenings that you see hot air balloons, because the air outside the balloon is cold and the air inside the balloon is hot. The cold air is more dense. So when you push that air out of the way, that weighs more than the weight of the balloon. So the weight of the fluid displaced is rho GV. Rho GV. Rho the fluid, gravity, times the volume of the object. The volume of the object is going to equal the volume of the fluid displaced. That's Archimedes' principle. Let's try a couple of these problems. All right, now this problem I had to shrink a little bit so the arrows are off, but a rectangular boat is shown below is occupied at the boat's on the verge of sinking. What's the maximum total mass of the people in the boat that'll keep it afloat? So we just learned that the weight has to equal the buoyant force if it floats, right? Just on the verge of sinking. It's not rising in the air. It's not accelerating upward. It's not accelerating downward. The acceleration of this system is 0. If you've ever been in a boat, you want the vertical acceleration. to be equal to 0. You don't want to be sinking or floating in your boat. So this is telling me that the buoyant force minus the weight equals 0. Well, our goal is to find this mass. We just learned that the buoyant force is equal to the volume of the fluid, or rho of the fluid, g times the volume of the object. We got a rectangular boat. The volume of a rectangle is length times width times height. So we can plug this in up here. Density of the fluid times g times length times width times height equals mg. G's are going to cancel. The mass equals the density of the fluid times the length times the width times the height. Oh, look, that's the volume times the density equals the mass. 1,000 times 4.5 times 2 times 0.3 equals the mass 2,700, it looks like. 2,700 kilograms. That's how much it can weigh. Pretty heavy. It's really heavy. Did I get that right? $2,700 kilograms. That's a 6,000 pound boat.
I don't trust a rectangular boat that is on the verge of sinking.
It weighs 6,000 pounds.
What if it's just those people that weigh that much? What if it's a light boat and really heavy people?
6,000 pounds of people, 3 of them.
I don't know if this is the scale or not, you know?
This sounds like a television series, a
They should
mockumentary.
contact Guinness World Records.
I don't know what's going on in this
Right.
boat, but
I might as well make it out of cardboard.
for 6,000 pounds.
Well, it's just how ridiculous this is getting. You might as well make it out of cardboard and it'll just sink on its own.
I don't know what it's made out of, but it's pretty big. I mean, that's a 15-foot boat. Maybe my little people that I put in there aren't the right, maybe I just drew it poorly.
If you add mass, wouldn't that displace more water?
Well, it's on the verge of sinking. I don't want to add any more mass to this boat. It
But
can only
say
hold
if you added balloons, those are technically have mass, but it's like it would make it float, right? So like, how do you?
What are you saying, you're tying a bunch of balloons to the boat?
volume?
Now each balloon would, now if you'd have to do this again, right? The balloons are all going to provide their own upward buoyant force, which is going to counteract the weight.
So the 2,700 kilograms is just mass with 0 volume.
No, it's the mass of this boat with these 3 people in it. Just this scenario, that's all. Just not really realistic numbers, but that's fine. All right. Any other questions on this? Any questions on the math or anything? Not the crazy problem numbers, but the math.
I guess it's just a matter of keeping the formulas handy.
That helps. All right, now this one's kind of tricky. Some fish have a density slightly less than water and must exert a force to stay submerged. So here we have an 85 kilogram grouper. What force must it exert to stay submerged in salt water if its body's density is 1015 kilogram meter cube? Now, salt water, the density of the fluid in this case is 1030 kilograms per meter cubed. the density of the fish, it's a grouper. So density of the fish is 1,115 kilograms per meter cubed. So that's fluid and that's fish. We know the mass of the fish is 85 kilograms. So here we got this fish. Right, fish is over here swimming away. I'm not too excited about that fish. There he is. And there's a buoyant force acting on the fish. I'm just drawing a free body diagram. The fish has a mass, mg, and it has to exert some force of the fish downward to keep it from floating to the surface. Our goal is to find the force of the fish. Are you ready? So the sum of the forces in the y equals 0. FB minus mg minus ff equals 0. FF equals FB minus mg. FF, remember our buoyant force, density of the fluid, gravity, volume of the fluid or volume of the object minus mg. Which are we missing? What variable are we missing from this equation over here on the right? Let's go through it one by one. Do we have the volume, the density of the fluid?
Yes.
Yeah, we know what G is. Do we have the mass of the fish, right? This is the mass of the fish. Yes, it's right here. And do we have G? Yes. So what are we missing? Don't everybody say the one that's not highlighted at once.
Yep. Well, V. Sorry, I just was.
V of the
misclicking.
object. So how are we going to find the volume of the object? The volume of the fish. That's what we need. We don't know the shape of the fish. We don't know the radius. We don't know if it's a cylinder. How do we use the density to find the volume? Haha.
The
So the volume of the fish equals the mass of the fish over the density of the fish. Would you like me to solve it here or plug it into the equation over there and make a crazy formula? Let's solve it here. I know the answer to that. I don't have to ask. 85 over 1015. The volume of the fish is 0.0. Let's do it in scientific notation. 8.37 times 10 to the minus second meter cubed. I don't know, I'm circling that. It's not a circle. We're not at a circle point. So now I have everything I need. FF equals the density of the fluid, 1030, times 9.8, times the volume of the object, 8.37, times 10 to the minus second, minus the mass of the fish, 85, times 9.8. What force does our fish have to swim down with? $12.31 newtons. 12.31 newtons. So our poor fish is tired at the end of the day. It's been swimming all day. No chance to rest. If it rests, it floats to the top. Pretty crazy, right?
I solved it a little differently.
Did you get the same answer?
Yeah.
Dare I ask, or you just want to roll with it?
Did you want to hear?
Sure.
I did 1030 divided by 1015 minus 1, and that gave me like a kilograms offset, like in percentage wise, and I multiplied that by 85 and then 9.8.
Yeah, because you just took this formula here. I'm just going to erase some stuff. You took this formula right here and you put it in here. So you had FF equals rho of the fluid G MF over rho F minus MFG. And you factored out the MF essentially. You can actually factor out the MG. And then you just have rho that minus 1. You know what I'm saying? That's what you did, right?
I think so. I just looked at it and I was like, can we write a proportion for this? Because the fish, it's got to be some kind of small percentage in comparison. So I tried to get that percentage by dividing.
Well, I think you did it right,
on.
but I don't think you knew why you did it right. I think you just logically figured it out, but I don't know if you could do it again. You know what I mean?
No. I know why it works. It's just
This is why it works right here. This is what you did.
yeah. There's all different variations that you can spin on the same formula, but you don't necessarily have to use the formula.
Oh yeah, you do. This is the formula right here. You just substituted this in. And if you had to do this again, there was another variable, you could still use this formula. But I know it makes sense to you and however you did it logically, but in the long run, you're going to have a better success rate if you go through the steps of the formula rather than just kind of guess logically. Does that make sense? There's a reason that this works there, and that's why it was equal to what you did. They're the same thing, but it's a good habit to understand the math behind it. Everybody ready for the quiz? Have we had enough? We got 10 minutes left. Here we go.
Should I factor in any possible fish that are in the water and their density or no?
No. It's saying that seawater is constant all the way down. All right, everybody have it written down so I can go to the chat.